In our previous video, we looked at two key concepts linked to our topic of electromagnetic fields. The first of which was magnetic flux density, which we represent by the letter B, and we said that magnetic flux density is equal to phi over A, magnetic flux divided by area, and that's measured in Tesla. And the second was magnetic field strength of a solenoid, and we said that was calculated by multiplying the current in the solenoid by the number of turns in the solenoid coil divided by the length, and that was measured in amp turns per meter. In this video, we're going to look at how these two ideas, or these two terms, are linked to one another. And they're linked by this formula here, which is B equals mu naught, which is that Greek letter mu with the little naught, H. So B equals mu naught H. Now we know what B and H are, but we have a new term here, mu naught, which is called the permeability of free space. Now, unfortunately, the permeability of free space has a fairly nasty value. It looks something like this. Mu naught is 1.25663706 times 10 to the minus 6. And the unit doesn't look very nice either. It's meters, kilograms, seconds to the minus 2, amps to the minus 2. Now, we don't need to worry too much about that unit. And we don't really need to worry too much about the number of mu naught either. It's a constant and it doesn't change, but we will need to refer to that number now and again when we're calculating B using this formula. Let's have a look at a quick example here, and let's imagine that I've got a coil here that is carrying a current I, and so that solenoid, that coil, is going to produce an electromagnetic field. And let's say first of all that I is 4 amps. So this coil is carrying a current of 4 amps. And let's say that N, the number of turns of the coil, is 500. And finally, let's say the length of this coil, L, is 10 centimeters. And I want to work out two things in this example. First of all, I want to work out the magnetic field strength, H, and then using our new formula, we're going to also work out the magnetic flux density, B. So starting with H, we know the formula for H is IN over L. And we can put our values straight in there because we can say, first of all, I is 4 times N, which is 500, divided by 10 centimeters, which in meters is expressed as 0.1 meters. And if we calculate that, I get an answer of 20,000 amp turns per meter. Now that we know H, we can calculate B because we have our new formula here. B equals mu naught times H. Well, mu naught, we said, had a value of 1.25663706 times 10 to the minus 6, multiplied by H, which we've just said is 20,000. And so, calculating that, I come up with an answer of 0.02513 Tesla. Now, we can better express that by multiplying by a factor of 1,000, which gives us 25.13 millitesla. The example that we've just looked at for a simple solenoid, or what we sometimes call an air core solenoid, is made slightly more complicated if the solenoid has a core. And solenoids often have a metallic core, such as iron, and that affects the magnetic field strength and the flux density. And it also affects our calculations as well. And so we have to take into account this iron core and the material that it's made of. So returning to our formula that we looked at the start of this video, we're going to add a new term in now called the relative permeability. And we give that the letter K. And so our formula now looks like this. B equals K mu naught H. This relative permeability, K, has been added in. And the reason this is called the relative permeability is because its value is relative to whatever material the core is made from. For the purpose of example, we're going to consider that the core is made from a magnetic iron, which has a relative permeability of around 200 in this case. If we imagine that this is the same coil as our previous example, just with the addition of an iron core, we can calculate our new magnetic flux density, because we can say that B equals K, which is 200, times mu naught, times H, which if you remember was 20,000 amp turns per meter. And this gives me an answer of 5.03 Tesla. If you remember on our last slide, we had a result of 25.13 millitesla without the iron core. So we've gone from quite a small magnetic flux density, 25.13 millitesla, to a much larger magnetic flux density just by adding an iron core. Let's go slightly further with our example, because we've said that we've calculated the magnetic flux density B to be 5.03 Tesla with the core in place. Let's say that I want to calculate the magnetic flux in that core. And remember from our previous video, magnetic flux is measured in Webers. And let's say that this core is a cylindrical core and it has a diameter of 1 centimeter. So we have a 1 centimeter diameter core, and we want to calculate the magnetic flux in that core, given that we know the magnetic flux density. Well, in our previous video, we saw that the magnetic flux density B can be calculated by phi, which was the magnetic flux, divided by A. So in our case, we want to calculate phi, the magnetic flux, and so we can rearrange that formula into phi equals B times A, the magnetic flux density multiplied by the area. But we have a problem here, because we want to calculate the area in question, which is going to be the cross-sectional area of the core. So, first of all, we know that the diameter of the core is 1 centimeter. And we also know that it's a cylindrical core, so it's going to have a circular cross-section. So the area of a circle is given by the formula pi r squared. And first of all, the diameter is 1 centimeter, which is 0.01 meters. And that means that the radius is going to be 0.005 meters. So my area is going to be pi times 0.005 squared. And calculating that, I get an answer of 7.85 times 10 to the minus 5 meters squared, because it's an area. So given that we know that now, we can return to our original formula here, and we can say that phi, the magnetic flux, is given by B. Well, we calculated B on the previous slide to be 5.03, multiplied by the area, which we've just said is 7.85 times 10 to the minus 5. Calculating that, I get an answer of 3.95 times 10 to the minus 4 Webers. Now, though our answer is correct, 10 to the minus 4 isn't really one of our standard unit prefixes. Our standard unit prefixes come in multiples of 3. So 10 to the minus 3 is milli, so milliwebers. 10 to the minus 6 would be microwebers. And so what we can do is we can convert to one of our standard unit prefixes by rewriting this as 395 times 10 to the minus 6 webers. And we know that 10 to the minus 6 is our standard unit prefix micro. So 395 microwebers would be our answer there. The last thing to mention in this video is the term reluctance, which is often given the name of magnetic resistance. We can kind of think of it as a measure of how difficult it is for the magnetic field to extend itself, any opposition that it faces. So we give reluctance the letter R as its symbol, but to differentiate it from, say, resistance, which also has the letter R, we usually write it in quite a scripted sort of style. And the formula for reluctance is R equals IN over phi, the magnetic flux. So we have this formula now for reluctance. Let's try and apply it to our example that we're currently working on. If you remember from the start of our example, we said that the current in our coil was 4 amps, and we said the coil had 500 turns. And finally, we've just calculated on the previous slide there that the flux is 395 microwebers. So putting all that into our equation here, we can say that IN is going to be 4 times 500, which gives us 2,000 on the top of our fraction there, over phi, the flux, 395 microwebers. Well, we have to express that in webers, so that'll be 395 times 10 to the minus 6. And if I calculate that, I get quite a large result of 5,063,291 amp turns per Weber. And using our knowledge of standard prefixes, we can say that that's the same as 5.06 mega amp turns per Weber. So I hope you found this video useful. First of all, to show the link between magnetic flux density and magnetic field strength. But then second of all, to show how we can calculate reluctance in an electromagnet.